In this last video, we're going to take a look at horizontal asymptotes, how to evaluate limits at infinity for rational functions, and then just do a kind of a quick recap of all, or rather both, vertical and horizontal asymptotes. So if either the limit as x approaches positive infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x equals b, then we say that the line y equals b is a horizontal asymptote of f of x. So if we look at the limit at positive or negative infinity and end up with a finite result, then that is the value of a horizontal asymptote. This is the definition that I'm going to use going forward. Some of you may remember from college algebra or a previous math class, you might remember, hey, if you can kind of look at the degree of the numerator and the degree of the denominator. And I'm okay with you using that information, but if I ask you to find the find the horizontal asymptotes, I need you to justify your answer in some way. So if you're using that information, you can just write a quick summary down saying, hey, I compared the degree of the numerator and the degree of the denominator smaller, so I know that I have a horizontal asymptote at y equals 0. And that's fine, that's enough. But we're going to look at some limits here at positive and negative infinity of rational functions. And when we're working with rational functions, we are just looking at the limit of the leading term. So this is going to be really similar to the polynomials that we just looked at in the last video here. So when I'm looking at limit as x approaches negative infinity, I'm going to look at the limit as x approaches negative infinity of my leading term. So I'm just going to take the leading term of my numerator and the leading term of the denominator. So the leading term in my numerator, I have 4x to the 7th is the term with the highest power of x. In my denominator, I have 6x to the 4th is the term with the highest power of x. And then from here, okay, we can take this and simplify. So 4 over 6, that's really 2 over 3. I know that's just a constant multiple, so I'm going to factor that out. 2/3 times the limit as x approaches negative infinity. Negative infinity. And x to the 7th over x to the 4th, that really leaves me with x cubed, or if you want to say x cubed over 1, that's fine too. And I want to look at this. Well, if I'm looking at the limit as x approaches negative infinity of x cubed, I know that this is 2/3 times this piece right here. I know that x cubed approaches negative infinity as x approaches negative infinity, so 2/3 times negative infinity gives me, well, still negative infinity. So I can just look at the term of the leading term of the numerator, leading term of the denominator, and then simplify the results. And then I end up with something that's very similar to what we were looking at in the last section. Part B, let me change colors here. I've got the limit as x approaches positive infinity of 5x plus 11 over 7x cubed minus 2. So I'm going to split this apart. Limit as x approaches infinity. I'm going to look at the leading term of the numerator, which is 5x. The leading term of the denominator would be 7x cubed here in this case. And I'm just going to simplify this. So 5/7, that doesn't really reduce, but that is a constant multiple. Anytime I have a constant multiple, I like to just kind of factor that out to the front. I think that's just easiest to do. You can leave it in there and it won't hurt anything, but I think it's easiest to see kind of what's going on if you factor that out. I want the limit as x approaches positive infinity. If I reduce my powers of x, I'm left over with a power of x squared in the denominator, so 1 over x squared. So remember that if x is approaching positive or negative infinity, and you're left with a positive power of x in your denominator, that means that this whole piece right here is going to go to 0. So if x approaches positive or negative infinity and you have any positive power of x in your denominator, that expression, that limit, will approach 0. And then, of course, the 5/7 just times 0. Here, in this case, 5/7 times 0, just 0 here. So that would be my limit in this problem. So to wrap this section up, then I want to just kind of summarize how to find vertical and horizontal asymptotes, because this is going to be a really important idea come later on in the course. So I don't need to do anything with these functions or with these vertical and horizontal asymptotes once I find them. I just need to go and find them. So first of all, I have f of x equals x squared minus 9 over x squared minus 4. Here, again, I'm going to start with the vertical asymptotes in this case, and if you can, I'm going to factor it. I think that's easiest to work with here, because then that also helps you identify whether you have a whole or a vertical asymptote. So x squared minus 9, that's x plus 3 times x minus 3, and x squared minus 4, that's really x plus 2 times x minus 2. So there's no common factors in my numerator and my denominator, so I'm going to take each factor of the denominator, x plus 2, and set it equal to 0. X minus 2 equals 0. So once I solve these two equations, I end up with x equals negative 2, x equals positive 2. These are the locations of my vertical asymptotes. X equals negative 2 and x equals positive 2. So now I need to go and find the horizontal asymptotes. And for that, I'm going to look at, well, what is the limit? And actually, why don't I do that in a different color? Let's do that in red. What is the limit as x approaches positive and negative infinity? Now, it turns out looking at just one should be enough, but I'm going to look at both here just to be safe. And the limit as x approaches positive infinity here, I'm actually going to use this unfactored form when I'm talking about horizontal asymptotes, just because it's easier to identify what your leading term is. So if I'm looking at x squared minus 9 over x squared minus 4, I can just look at the leading term of the numerator and the leading term of the denominator. So the leading term of the numerator is x squared. Leading term of my denominator is also x squared. So what I really have is the limit as x approaches infinity of 1 after those simplify. Well, 1 is just a constant. It doesn't depend on x in any way, so that means I get back a y value of 1. There's my limit. So that means that y equals 1 is a horizontal asymptote. I would like you to include that y equals part so that we can see, oh, that's the equation of the horizontal asymptote. Similarly then, if you want to look at the left-hand end behavior as well, the limit as x approaches negative infinity of f of x here, again, I'm just going to look at the leading terms. Limit as x approaches negative infinity, x squared over x squared. I know that that's going to end up being, sorry about that. Limit as x approaches negative infinity of 1, this is equal to 1 here. So I end up with the same value, which means that this is still just a horizontal asymptote. Part B, I have g of x equals x plus 5 over x squared. So again, I would say factor that if you can. In this case, well, it can't really factor any further. So I'm just going to take my denominator, set that equal to 0. X squared equals 0 gives me x equals 0. So this is my vertical asymptote. So there's the first part of my problem. To find the horizontal asymptotes, again, I'm looking at the limit as x approaches positive infinity, let's say of g of x here. So I'm just looking at the leading term of the numerator and the leading term of the denominator. So limit as x approaches positive infinity, leading term of my numerator is x over x squared. We can, of course, simplify this. This is limit as x approaches infinity here of 1 over x if we cancel that common x. And I know that this piece right here approaches 0. I have a positive power of x in your denominator, means that whole thing goes to 0. So that means that y equals 0 is a horizontal asymptote. And then we should probably check the left-hand end behavior too. It's not very common that you'll have two horizontal asymptotes, but it's probably a good habit to check, and if anything, it's just a good little bit of extra practice. So here, limit as x approaches negative infinity of g of x. This is the limit as x approaches negative infinity. I know, again, I'm just looking at the leading term of my numerator and the leading term of my denominator. Here you can kind of look up above. I already done this work, so limit as x approaches negative infinity of x over x squared. I know that that's going to go to 0. So I still have a horizontal asymptote of y equals 0. There's not an extra one to add on here. All right, last example here. I have h of x equals x squared plus 11x plus 10 all over x plus 1. Again, wherever you can factor and simplify, I think it's a good idea to do so. So let's see, two numbers that multiply to be positive 10 and add to be positive 11 would be x plus 10 times x plus 1, all divided by x plus 1. We see that common factor in that numerator. Remember that if you take that, though, set it equal to 0, because that was a common factor of both your numerator and your denominator, this is not a vertical asymptote. Instead, this is the location of a hole at x equals -1. So I didn't ask you to find that here, but I just wanted to make sure that we address that this is actually a hole and not a vertical asymptote. So if I don't have any factors of x in my denominator, right, because I'm left with really just x plus 10 over 1, which is x plus 10, I don't have any factors of x in my denominator, so that means for me that I have no vertical asymptotes for this problem. But it might still be possible for me to have a horizontal asymptote. So here in this case, let's look at the limit as x approaches positive infinity. Again, I'm going to use this unfactored form. It's easier for us to look at that unfactored form because it's easier to identify the leading terms. So the leading term of my numerator is x squared. Leading term of my denominator is x. So I have limit as x approaches infinity of just x. Well, if x approaches infinity, then this x should also approach positive infinity. And if I end up with a value of positive or negative infinity, what that means is, at least on that side, for that particular end behavior, I don't have a horizontal asymptote. But maybe we'll check the left-hand end behavior just to be safe. Limit as x approaches negative infinity. Here I have x squared over x. Again, this is limit as x approaches negative infinity of x. Well, here x approaches negative infinity. So again, I did not end up with a finite value on either side for the left or the right end behavior. So what that means for me is that I have no horizontal asymptotes here in this case. So in this case, there are no vertical asymptotes and there are no horizontal asymptotes. This is going to be an idea that we absolutely come back to in Chapter 4 when we talk about graphing functions. We need to be able to identify where we have vertical asymptotes and horizontal asymptotes. So this is something that we are going to revisit later in the course.